you've seen that any surface can be cut up and flattened into a polygon, from which we can write down an algebraic equation called the edge equation, which represents the surface. Now, for each surface, there are lots of different polygonal representations giving different edge equations. But as you know, there's an algebraic procedure which singles out a particular equation for each surface called the canonical edge equation. What we're going to do is to look at every possible canonical equation and interpret it geometrically. That is, we'll see what every possible surface actually looks like. So first, let's remind ourselves what all the equations look like. Every orientable surface has a canonical equation of this form. We've replaced the -1 by a bar to make things easier to read. And every non-orientable surface has a canonical equation of this form. For example, here's a specific orientable surface where p equals 2 and r equals 1. It has 2 blocks of symbols of this type and 1 of this type. Now, what do all these surfaces look like geometrically? Well, you may have recognized that these 3 types of block correspond to 3 familiar surfaces. They form the canonical equations of the torus, the projective plane, and the disk. Well, it turns out that every possible surface can be constructed geometrically out of these 3, plus 1 extra surface, the sphere.
The method of construction is one you met in an earlier program. Remember, we took 2 Möbius bands, cut a disk out of each, then we pushed out the edges of the holes towards each other and glued them together. We can do this for any 2 surfaces, L and M. Cut a disk out of each, and then curl out the edges of the holes and glue them together. The new surface is called the connected sum of the surfaces L and M, and we write it like this. By the way, it doesn't matter in which order you take the surfaces. In other words, the construction is commutative. So that's our construction, and we can do it repeatedly. We can now take this surface and form its connected sum with another surface, like this. So we now have the connected sum of 3 surfaces, L, M, and N, and so on. Let's now look at connected sums which specifically involve our 4 basic surfaces. We want to establish that by taking connected sums of copies of these, we can construct every possible surface. So we'll need to calculate the canonical equations of connected sums of these. But before we go back to the algebra, let's do some exploring geometrically. Let's see what happens if we take a surface which we've got already and form its connected sum with each of these in turn. Let's start with the sphere. You've already seen the connected sum of the sphere with the 2-hole torus, but topologically this is still the 2-hole torus L. You simply have to shrink the sphere and push the tube in. You can see, in fact, that this argument doesn't depend on using the 2-hole torus. The connected sum of S2 with any surface L is homomorphic to the original surface L. So we don't get anything different if we add a sphere to a surface. We've included it here just to represent itself. Setting it aside for the moment, I'm now claiming that all surfaces other than the sphere can be constructed from just these 3. So let's continue exploring with each of these. What do we get if we form the connected sum of a torus with an arbitrary surface? Well, the result looks as if you've attached a handle to the surface. To illustrate that, consider the connected sum of a torus with a Möbius band, say. We cut a disk out of each surface and we have to glue the edges of the holes. But before we do that, I want to show you that we can deform this torus minus disc into this shape. So a torus with a disc removed is topologically equivalent to this, where this boundary comes from the edge of the original hole. So to get the connected sum, we have to glue this edge to this one on the Möbius band. So we'll have to reduce the size of this to something like this. And here's what we get, a Möbius band with a handle attached. Let's now consider the disk and see the effect of forming its connected sum with an arbitrary surface. The effect is quite surprising, because when you take the connected sum, you might expect that you'd be adding something to the surface L, whereas topologically you've actually removed something. The surface L has ended up with a disk actually cut out. To put it another way, taking the connected sum with a disk has the effect of constructing a boundary curve. Finally, the projective plane. What happens if you form the connected sum of this with an arbitrary surface? Well, the most important feature of your new surface is that it's non-orientable. That is, it contains a Möbius band. Let's see why. In forming the connected sum, you're cutting a disk out of each surface and gluing the edges of the two holes. We'll denote the gluing like this. But remember that RP2 with a disk removed is a Möbius band whose boundary is the edge of the hole. So when you glue this boundary to the hole in the surface L, you're gluing on a Möbius band. Therefore, the connected sum is non-orientable.
Let's now go back to our original assertion that every surface, except the sphere, is a connected sum of copies of our three basic surfaces. We've been hinting that an orientable surface with P blocks like this and R blocks like this is the connected sum of P copies of a torus and R copies of a disk. Similarly, a general non-orientable surface is the connected sum of Q copies of a projective plane and R copies of a disk. Well, in order to prove those assertions, we need to show that when you take connected sums of copies of these three, then an edge equation of the connected sum can be obtained by putting the corresponding blocks of symbols side by side. For example, if we take a torus with a disk, then this is an edge equation for their connected sum, just putting the two blocks side by side equal to 1. Well, that's true for any number of copies of the torus and the disk, and also of the projective plane and the disk. The proof's algebraic, and you can try it later for yourself. So taking that as proved, we get the promised result. A surface with P blocks like this and R blocks like this is the connected sum of P toruses and R disks. We write it like this for short. Similarly, a general non-orientable surface is the connected sum of Q projective planes and R disks. So that's finally interpreted all these surfaces as connected sums. And we're now ready to do what we promised and show you what surfaces actually look like. For the orientable surfaces, you've already seen several examples which look like connected sums.
For instance, one of the surfaces we looked at earlier was the two-hole torus, which is in fact the connected sum of one torus with another. This is fairly obvious, but let me look at it in a slightly different way that will help us later on. To form the connected sum, we have to cut a disc out of each torus and glue. But remember that this is also a torus with a disc cut out of it. So the connected sum is a torus with a handle attached, which is just a slightly deformed version of the two-hole torus. So that's one orientable surface. What about this surface, the connected sum of two toruses and a disc? You've seen this surface too when we illustrated that taking a connected sum with a disc is topologically the same as removing a disc, that is, constructing a boundary curve by making a hole.
So now we know what every possible orientable surface looks like. It's got P handles and R boundary curves. The torus, P equals 1. Two-hole torus, P equals 2, and so on, with any number R of discs removed, that is, any number of boundary curves. And if P equals 0, so that there are no handles, then R equals 1 gives the disc. R equals 2, the disc with a hole cut out. R equals 3, the disc with two holes, and so on. And of course, we mustn't forget the special case we mentioned earlier, the sphere. It's orientable, but it has no handles and no boundary curves. That's why it can't be constructed using our other three ingredients. And it doesn't have an edge equation of this canonical form. So now for the non-orientable surfaces, connected sums of projective planes and disks. For the cases where R equals 0, the surfaces don't have a boundary. And as you know, if a non-orientable surface doesn't have a boundary, it can't physically be constructed, because it can't be embedded in 3 space. So we can't show you what such a surface looks like in its intact form, but we can look at polygonal representations. First, there's the projective plane itself. Then, for Q equals 2, we get a familiar surface. Remember that removing a disk from RP2 gives a Möbius band. So when we glue the holes to get the connected sum, we're gluing 2 Möbius bands along their boundaries, which gives a Klein bottle. Before I look at any more non-orientable surfaces without boundary, it's more interesting to look first at those which do have a boundary. The point is that every surface which has a boundary can be embedded in 3 space, so we can show you what all of them look like. In fact, I don't need to cover the cases when R is greater than 1, because each extra disk you add just gives you another hole, and that's easy to visualize. So let's start at the beginning with R and Q both equal to 1. This is very easy, because we're just removing a disk, remember, which leaves a Möbius band. What about this? Well, you've just seen that 2 projective planes make a Klein bottle. So what we've got is a Klein bottle with a disk removed. And unlike the intact Klein bottle, this can be embedded in 3 space.
And here it is in real life, the Klein bottle with a disc removed, the connected sum of 2 projective planes and a disc. What about 3 projective planes and a disc?
Well, we can split this up into 2 surfaces you've seen already, the Klein bottle and the Möbius band. And we have to cut a disk out of each and glue the holes together.
But how do we do that? Well, at first sight, it doesn't look possible to glue the edges of these holes to one another. But in fact, the Klein bottle minus a disc can be distorted into this shape. And this can be glued into here. But before I show you the gluing, let's see how this distorts into this. So this is a Klein bottle with a disc removed. And if we reduce its size, then we can glue it into this hole. And we get this surface. The connected sum of a Klein bottle with a Möbius band. That is 3 projective planes and a disc. The Klein bottle is 2 projective planes, remember, and the remaining projective plane with the disc is a Möbius band. Well, I haven't quite proved that yet, because you may have noticed that you can't physically glue these together. But it's clear that you can do it if you make a temporary cut in one of them and then push this in and re-glue the cut. By the way, you'll see in a moment that adding a Klein bottle is a crucial operation, so bear in mind what it involves. You have to glue in one of these into a hole cut in the other surface.
In fact, that operation turns out to be just what we need to describe the rest of the non-orientable surfaces with boundary. They fall into 2 types, those with Q odd and those with Q even. For Q even equal to 2n, we get the connected sum of n Klein bottles with a disc. That's because each pair of projective planes gives a Klein bottle, as you've seen. Then for Q odd equal to 2n plus 1, the 2n projective planes again give us n Klein bottles, and that leaves 1 projective plane and a disc, which you've seen is a Möbius band. So that's the formula. Now what do these surfaces look like? Let's take the odd case first. N equal to 0 just gives a Möbius band. And I've already shown you this. Then n equals 1, giving 3 projective planes, is the sum of 1 Klein bottle and a Möbius band, which you've also seen before. And the remaining odd cases will be quite easy to visualize once we've shown you the next one in the sequence, n equals 2. The connected sum of a Möbius band with 2 Klein bottles.
Well, you've just seen the connected sum with 1 Klein bottle. So we just have to cut a hole in this and glue in another one of these. And here's what we get. 2 Klein bottles with a Möbius band. And you can see what will happen in general. Every time you increase n by 1, you add another Klein bottle. So that's dealt with the odd numbers of projective planes, and the even case is just as easy. This time we take a disc instead of a Möbius band and add Klein bottles to it. So for n equals 1, we just have 1 Klein bottle and a disc. So we have to cut a hole in this disc and glue one of these into it. So all that happens is that this flat piece gets enlarged, like this, and we've enlarged the tube as well. So we've done n equals 1. For n equals 2, we have to make a hole in this and glue in another one of these. And for n equals 3, we have to glue in a third one, and so on. In fact, I've got the one for n equals 3 here. That's 3 of these glued into 3 holes cut into this disc. In general, for an even number of projective planes, then, we just have a disc and n Klein bottles instead of 3. And that does it. The non-orientable surfaces with a boundary are of two types, either a disk with Klein bottles or a Möbius band with Klein bottles.
So you've finally seen what every embeddable surface actually looks like. There's one extra question. What happens if we take a connected sum of surfaces, one of which has handles and the other projected planes? That's a non-orientable surface, so we know we must be able to express it like this without any toruses in the expression. You've seen how to do this algebraically. For example, this edge equation reduces to this canonical form. In other words, the connected sum of one torus and one projected plane is equivalent algebraically to 3 projected planes. Now there's a problem in seeing that geometrically. We can't see the surfaces themselves embedded in 3 space because they don't have a boundary. So what we do is to make a boundary in each by removing a disk. Then we can physically construct these new surfaces and then show geometrically that these are homeomorphic. Finally, we can retrieve our original surfaces by gluing the disks back on.
Well, you've seen these new surfaces before, and here they are. The Möbius band in each case is one of the RP2s with the disk, and the Klein bottle here is the remaining 2 RP2s. And to prove these are homeomorphic, we just have to move this end of the handle. So these two are homeomorphic. Therefore, gluing a disk back onto each retrieves the original surfaces and proves that they are also homeomorphic. In fact, this shows that any mixture of T2s and RP2s can always be expressed in terms of RP2s alone.